Okay, so it's just about
So,
it.
yeah.
Okay.
And that's how you do it.
Yeah, we should like make a presentation.
Yeah.
Like,
I can do it over two people.
yeah, we could do, because like most of the paper, so it's
Yeah.
like that.
Okay.
Okay.
So we're going to continue talking about Bayesian methods, and we'll see a little bit more about that beta prior binomial likelihood and what we can do with that, more along the lines of what's on the homework. So questions about that. And then look at another version where the data was on, we use a different type of prior for that, and then see what the posterior does. Example. This has an aside. There's various books on Bayesian statistics, but a few years back there was kind of this popular book, Sharon Brain, Theory That Would Not Die, How Bayes' rule of cracking input code, how to deal with Russian submarines, and emerged widely after 2 centuries of controversy. It's a pretty well written book. I wrote a review of it at one point, and found it interesting and to give some insights of development of probability theory and things during the 1700s, 1800s, how things changed with computing and algorithms that make harder problems possible, and then kind of a variety of different places this has been used. So I thought it was kind of an interesting read, not too technical, but having seen what Bayesian statistics is, getting some appreciation for kind of how it's fit in, it could be kind of interesting. So, but anyway, that's kind of an interesting book I thought I'd just mention. And today we're going to talk about this. So we're going to review a little bit of this beta binomial and then go look at a new case. And so in this beta binomial, we're interested in a proportion. So the parameter we're interested in is a proportion. It's between 0 and 1. It's a probability of success, a probability of something happening that we're interested in. The prior distribution we're going to use is P is going to have a beta distribution with parameters alpha and beta. And so one thing we can try to, depending on the question we're asking, what is P, what's its context, is that we need these two values here. We need these alpha and beta. Sometimes these are called hyperparameters. They're kind of hyperparameters. They're kind of parameters of our prior. So they're kind of a next stage out of that, right? So let's say we're going to ask a survey question, right? Do you support $1 per gallon tax, right, to offset greenhouse emissions? A $1 tax, might seem like a lot. The price of a gallon everywhere else in the rest of the world is pretty much higher than it is here in the U.S. I mean, a few years ago, gas was $4 a gallon. Now it's $2.50 again. Go figure. But, there's a number of reasons for that: production in the U.S. and price supports and other things that we're paying for. In places like Europe, it's quite a bit more. So $1 would have its impacts, but depending on how serious you think this is, that the problem maybe somebody might support that. So we're going to ask adults this, and we need to put and we're going to get a bunch of responses. They're either going to say yes or no. So we're going to get a sample estimate proportion, but before we do that analysis, we should think about a prior distribution, right? Well, one way to think about that, to choose alpha and beta, is we could think about what do we think the expectation would be. Under the prior, the expectation is alpha plus beta. Do you think 30% of adults would say, yes, I would support that? Maybe that would be less than 50, taxes and paying more money, but let's suppose you think it's 30%. How confident, how sure are you of that number? What would be the range of things you would think would be possible? Right? the variance under this prior distribution, yeah. Try to get this thing to cooperate here now. The variance of a beta is this is the formula that you can figure out from in probability theory. This thing looks complicated, but there's an alpha over an alpha plus beta here, which is 0.3 according to this. And there's a beta over alpha plus beta. That's 1 minus the other one. So there's a 0.7 here. Kind of a p times 1 minus p proportion type of thing going on. And then alpha plus beta plus 1 down there, right? That simplifies it a little bit. Where do we think this number is going to be, right? So if it's 0.3, what if it's between, something like, point, 1.5 up to about 0.45. Or maybe 0.114 up to 0.46, something like that, right? So, that'd be a standard error, kind of a half width of that interval, that's plus or minus about 0.75 or 0.08. Do we think that our response is going to be somewhere in that range, right? Maybe if it's below 0.14, we'd be kind of surprised. At least, 1/8, 1/9, something like that, other people are going to say, yeah, we would pay that tax, but we'd be surprised if it were much more than 45% saying that, right? So you could do some assessment and say, what would really surprise you? Where do you think it's really going to be? But this would suggest, this last one would suggest the standard deviation is about 0.08. Right? The half width is 0.16, and that's kind of 2 standard deviations, right? So this is like 0.3 plus or minus about 2 standard deviations would give that as we are kind of think the answer is going to be, right? So if that's the standard deviation, we can make that equal to the variance, right? So now we have 2 equations, right? This one and this one, and we have 2 unknowns, alpha and beta, right? So if we solve, we should get the parameters alpha and beta that are consistent with this mean and variance from our prior opinion. And so it's not too bad to do this. One thing you could do so what we're going to do now is solve for alpha and beta in this. I'll do it on the next page. The expectation was alpha over alpha plus beta, and that was 0.3. So that implies that alpha is 0.3 times alpha plus beta, or alpha plus beta is alpha over 0.3. Right? The reason I'm doing that is the variance, which was 0.3 times 0.7 over alpha plus beta plus 1, is at 0.08 squared, which is 0.0064. And if we multiply this over there, 0.3 times, well, that's 0.21, so right? That's 0.21, and then it's 0.0064 times alpha plus beta plus 1. Right? And here we have alpha plus beta, so if I put that in there, that's just alpha over 0.3 plus 1. And now I have an equation with just alpha in it. And so if I do the algebra there, I get an alpha value of 9.54. Working that out. And if then I go back to this equation and put the 9.54 in there, we just have beta. Or rather, beta's up here too. So if we plug this one in, right, this would say beta is alpha over 0.3 minus alpha. Right? So plug in alpha into that, and I get beta is 22.3. And so that should work out to give the mean and variance that are consistent with that kind of prior opinion. If you disagree with that, you can set up your own mean, your own standard deviation based on what you think. If you feel, no, people won't pay that, move your mean down, maybe make the range shorter. If you say, I don't know, it might be higher, I think I want a wider range to account for all possibilities, you'll get different parameters. We can graph that. So I set up just a sequence of numbers from 0.01 up to 0.99. Here's actually the value of p, all those numbers there. And then I'm going to plot p versus the density, that's the binomial height of the curve, with those two parameters. And I make it a line. And oops. So that gives this picture over here. So my probability density a priori is like this. Right? And as most of the evidence, between about 0.1, 0.15, 0.6, something like that, up to about 0.4. Yeah, so it's a little bit, it seems to roughly match. The binomial is not exactly symmetric. I kind of went through the reasoning with kind of a symmetric thing with the standard error. It's a little bit different, but that's pretty close to, you're pretty sure it's going to be in this area. That's where our prior should come from. Right? So one of the homework problems as you're given a mean and a standard deviation, or a mean and a variance, and you go through a little bit of solving. There's multiple ways to solve that equation for alpha and beta, and if you kind of keep track of where you're trying to go, you can solve it different ways and not take too long to do it, right? But let's say now a survey is done. So a survey is done, and we have 200 people in the survey, and we get 52 that say yes. Our sample proportion, 52 out of 200, is 0.26. So this means n minus x is 148. No, they wouldn't pay that. One way to report an inference for p would be simply do a 95% confidence interval. Yeah, and that 95% confidence interval, using the formulas we've used, 0.204 up to 0.325. Around there. The Bayesian is going to update from the prior distribution to the posterior distribution, and then summarize that. Right? Where did this number come from, these? So in R, right, if you did the crop test and said X, we had, 52 out of 200. And I'm not going to use the continuity correction.
You said correct is true.
Correct is true, correct is false. Right. So is that what I wrote down, 0.204 up to 0.325? So that's where I got this confidence interval, just from that. But a Bayesian is going to update the prior distribution. We're going to write down the distribution for P given our data. And we figured out last time that that's another beta distribution where you take alpha plus the number of successes and beta plus the number of failures. And so the distribution that expresses our knowledge after seeing the data for this prior alpha was 9.54, and then X is 52, and then beta was 22.3, so we got 148 as the number there, right? And the estimate, the posterior mean, if we need to so kind of the p-hat, the Bayesian estimate of this, is we'll take the 9.54 plus 52, the first parameter, right, over the sum of those next two. So a priori 9.54 plus the 22.3, like 8431 in there. So like 31.84 plus our 200 people. That comes out to be about 0.265. So the Bayesian estimate is a little bit above this sample proportion because this is kind of a blend, right? It's your data, but your prior opinion was 30%. The data ended up being a little bit lower, so you don't go all the way down to the data, you kind of blend them together. And if that prior really meant something, and you really thought about it, and it was kind of seemed like a reasonable summary, that would be kind of reasonable to do. But you can get the central 95%. Sometimes this is called a posterior interval, or sometimes people call it a credible interval, because it's not a confidence interval, right? Just to use a different word, but it's a posterior probability interval. And so if we do the quantiles for beta, right, 0.025 and 0.95 points for that, we put in our parameters, 9.54 plus 52, and then 22.3 plus 148. Right, that should give us some intervals, 0.207 or 0.211 rounding it, and 0.314. So our Bayesian intervals ends up being 211 up to 0.324. And so that's pretty close to the confidence interval, right? 211, 324, and before we had 204, 325. Right? It looks like a little bit narrower because you're keeping some prior information along with the data, so it's like you have a little bit more total information. And it's shifted a little bit, just slightly from that. So now they do another round of the survey. Another 100 people come along, right? And they ask them the question, what do we do now? Into 100 people are asked, and for these two, we get 40. What do you think a Bayes person can do?
Update?
Yeah, there's an update, right? We had a prior that was beta, and then a binomial likelihood, and that gave us a beta posterior distribution. Well, that's a beta probability distribution.
Then we treat that
Now
as
we get new data, multiply it in, update it again, use what, the first posterior distribution as our new prior, right? Update it with more information. And so, after survey 1, P we thought was distributed as a beta distribution, and we had that 9.54 plus 52 as that parameter, and this one is 22.3 plus 148, right? And now we get x2 as 40, and n2 minus x2 is 60, because there were 100 total. So now this, given our x2 data, maybe you want to call this given x1 to emphasize that we've already had some data. This one could be called P given x2 and x1, right? Conditional on more information. And so the same process is going to happen. We're going to take this prior number here, kind of intermediate one, and now we're going to add 40 more to it. So 9.54 plus 52 plus 40. And then this one, 22.3 plus 148 plus 60. And we'll get a new prior. In this case, the posterior mean of this one is closer to what we a priori had thought, because I made up the numbers. There you go. And the 95% posterior interval B for Bayes, 95% posterior interval for P. Just like the confidence interval is a confidence interval for a parameter, these intervals are telling us where we think the parameter is, conditional on the data. I calculated it as 0.258 to 0.357. So it's shifted because of the new data, pulls it one way. It's a combination of the two data sources and the prior. This is narrower. Right? As we get more data, confidence intervals get smaller and things like that. Get smaller. And in the Bayes, it's a pretty straightforward calculation to add new data in. Does it matter which order the surveys come in? Not for the final answer. Right? If we had another survey, we just could keep adding it in through the same calculation. What do you do for a confidence interval exactly? You have one survey, two surveys. You have in1 was fixed and in2 was fixed. How do you do that exactly? Well, it's not really that too bad. You probably do a weighted average of the two sample estimates. But how do you do your bootstrap if you wanted to study that, or your simulation to get standard error? I mean, in this case, the math wouldn't be too much, but you know, there's a little bit of thinking. Well, do I need to take into account how I gathered the data, and would I gather data the same way in the future, and things like that. Bayes kind of sweeps that under the rug by dealing with the probability formulas directly. It's a little kind of subtle or you know, deep or appealing to some other kind of rationale for kind of preferring one to the other, but the Bayes focuses. It's really through that likelihood. You multiply independent likelihoods together and put a prior on the parameters and figure out what you get in the end. And so it's a little more direct. The likelihood approach, like maximum likelihood, is also kind of the same way. You have the likelihood of these two independent things, you multiply them together, and you maximize them. So those things that give you, kind of take some of the choices out a little bit. The likelihood, still you'd have to think about sampling, figuring out bootstrap, or what exactly is the properties of these things. It's not quite a straightforward way to do it. You have to kind of think about it case by case. Right? But anyway, so this would be an example of, you know, Bayesian analysis and learning from the data. Some design issues produce the same, you know, Bayesian analysis. Right? So we've talked about doing a binomial sample, right? So in binomial sample, right, the probability that x equals some value is this n choose x, p to the x, 1 minus p to the n minus x. In this type of sampling, n is fixed. Right? You count a number of trials and you count up the number of successes. Right? And x is the number of successes. There's another type of sampling, right, called negative binomial. Where you sample until you get R successes. X equals number of samples that, there's different ways of calling it things. It could be the total number of samples or the number of samples that are failures until you have R successes. The total number here, x plus r, right, is not bounded. You could have to keep going forever just to get r successes, or for a very long time, or it might happen quickly. You don't know how long you're going to sample. The probability for x in this case, well, there's a p to the r, 1 minus p to the x over here, and then there's a combinatorics, kind of x plus r, and then cases like -1 or -1. The last one has to be a success. So there's a combinatoric thing out here that's a little bit different. Well, both of these models have a proportion between 0 and 1. So we could use a beta prior distribution for either one, right? It's a reasonable thing for that. If p is distributed as beta, what is the posterior distribution of P given our data? Well, there's something nice about Bayesian analysis in the sense that if this likelihood piece is up here, if here R is the same as X, and this thing is the same as that, so let's not make that quite so confusing. We call this Y. Y is the number of samples. And then this data Y over here. This is the Y, and this is the Y. For those of you writing pen, I'm sorry about that. Change that, but so Y is the number of samples until failures, and we do Y plus R total in there. So if it turns out that things line up and you get the same number of successes and failures, right, in these two scenarios, if it turns out that you got X successes here and you planned on that number of successes down here, and the number of trials you had to do to make failures ended up matching up that. If these two things match up, you have the same kind of core part of this likelihood, and the prior is the same. And the Bayesian analysis is going to give you the same result. Right? It ends up, you do that probability calculation, and you end up with the same answer, the same posterior distribution. So in some cases, this Bayesian analysis doesn't really care so much about the sampling results, about how it was done. It's looking at the results as they come in. And so that can be kind of nice as well. There's some of these things with frequency statistics and thinking about it in likelihood. Well, you kind of have to think about how it was done and use a different likelihood function a little bit. Like maximum likelihood kind of fixes some of that too, but in other things about what's the expectation, and these models have different expectations and different method of moments estimators, and so they end up being a little harder to tell. So the Bayes. Okay, so if X is the same as R and the N minus X is the same as Y in these things, then Bayes answers are the same. Are equivalent. Are the same under those two scenarios. So you can have two different sampling things and it still works out to be the same. So there's some nice things that happen with there. So it reduces things to what's the probability statements, and if the core part of the probability statement is the same kind of kernel. Sometimes it's called the kernel of the probability function that involves the parameter, then it's the same. Well, let's look at one more example. I want to look at some Poisson data and a gamma prior to see how that one worked out, right? Get a little experience with data. But any questions? It's maybe a little bit vague because we didn't run through an exact example, but there's a few other aspects that make it desirable as a theory. So the next the second kind of main one we're going to look at is our data are going to be Poisson. So X given lambda is going to follow a Poisson distribution. So X can be 0, 1, 2, etc. And the probability that X equals some count given lambda is our lambda to the X e to the negative lambda over X factorial. And that would be the calculated probability. That's going to be some number between 0 and 1. You add those up over all the x's going out to infinity, and it adds up to 1. Most of the probabilities in the low numbers, so out past 1 million, you're not going to see that in any likelihood, but so on, right? And so the question is, what is, you observe a count, and the question then is, what is lambda? What is the rate? What is lambda? What is that parameter? Right? And so a prior that can be used for this is called a gamma distribution. Now, the prior distributions represented here are not the only ones, right? You can use a lot of different things as prior distributions. Lambda is restricted just to be a positive number, so a prior for lambda should put support on the real numbers. It'd be possible to do a uniform number, not from 0 to infinity, because that doesn't integrate to 1, that's infinite. You could put something on, say, 0 to 1 million. Say, I don't know where this is, but I think it's less than 1 million, so 0 to 1 million flat, right? That could integrate to 1 at the proper height, and that would not be a gamma distribution. So you could choose other priors, but a prior that says gamma is not above 1 million has a consequence. You're not going to get an answer that's above 1 million because your prior has excluded it. So anyway, this is one. The prior probability for a gamma, right, is a function 1 over gamma of alpha, beta to the alpha, and then lambda to the alpha minus 1, e to the negative beta lambda. We have an appendix in the book that has some of these distributions. You don't need to memorize these for any exams or anything like that. I likely will put some Bayesian calculation on there where you put a few of these things together, but I'll give you a formula like this and then you'll work with it a little bit. So the shape of this thing for different alphas and betas is something kind of like that. The expectation of this parameter, a priori, from this prior distribution is alpha over beta, and the variance of lambda is alpha over beta squared. The expectation of x under its data model, right? The expectation of x to constant, x given lambda, which is lambda, right? So we expect lambda responses from that distribution in there. But these are our variances, right? And then we're going to figure out the variance of what happens. So let's think about a problem and think about a prior distribution, right? So how many babies are born per day in the University of Vermont Medical Center? So UVM Medical Center. Don't Google on your phone. No babies per day. What population are we dealing with? Certainly Vermont, parts of New York probably. Massachusetts is a little far to go. New Hampshire, maybe some would come over, but so that's kind of the population. 365 days. How many do you think are born in a year? Okay. So let's take your professional opinions of this, right, and get some kind of prior data, and we'll use that to produce an alpha and a beta. How many do you think are born per day? Any guesses?
45.
45. Right. And the others? 20. Right. So, any other guesses? You don't necessarily have to be
30.
30. Okay. Right.
63.
63?
Yeah.
63.
25.
So let's so what's the average of these, right? So 45
How many people died today?
45 plus 20 plus 30, and then this was 63 and 25. 63 plus 25, and that was 5 opinions, right? So that's about 36.6 per day, right? So 36.6 for 365 days would be about 13,000 babies. You think that many are born there? Maybe, you know, it's a medical center. So that's an average, 36.6. What's the variance of those numbers? Right, so 45, 20, 30, 63, 25. The variance of those is 305. Right? The standard deviation, right, is on the scale of measurement. So kind of plus or minus 17, plus or minus 34. That's kind of so. But you know, you can some Bayesian applications get experts solicit opinions. Some more advanced ones in psychology would say, where's your estimate? What are you kind of 95% intervals? What do you think would be surprisingly low, surprisingly high? And kind of ask a few more questions. So if we have 36.6, right? So alpha over beta is about 36.6. If these things are kind of our prior observations, and alpha over beta squared as a prior, what did we have? 305.3, 305.3. Then this one over this one is beta. This one, 36.6 over 305.3 would be an estimate for beta. And then alpha is going to be beta times the 36.6. So that must be 36.6 squared over 305.3. Is that right? So this one over this one, the alphas cancel. You have 1 over beta, and then in the denominator you have 1 over beta squared. So you get a beta flipped up to the top. So those would be something like our prior values. 36.6 over 305.3. And then that times 36.6 for beta. So we're getting an alpha of 0.12.
Beta?
No, beta of 0.12. Right. It's beta 0.12, and then alpha is at 4 something. Alpha is 4.4. So this is 0.12. Right, so we can make a little plot of that. So if our x values, well, this is for our lambda, so lambda, right? I'll just call it lambda. We do kind of a sequence of, 0.1 up to, like 400. Let's do that by 0.1. It's a lot of numbers, but it's fine. So we plot the lambdas and the density for gamma at those values. And now our numbers, 4.39 and 0.12. Let's see what this looks like. So it looks like something like that. Our average, 36 is in here, 36.6. Standard deviation, 17 plus or minus about 30. So 30 is in here, plus or minus about 30. Kind of, we're saying kind of a priori, we think it's kind of like that. Now let's get some, now we're going to get some data. We got to figure out what the answer is. So if lambda has a gamma distribution, and then x given lambda is Poisson lambda, and it turns out that lambda given x ends up being, well, we're going to write this down. The density for lambda given x, we look at that probability density. It's the density, the prior density for lambda, the probability for x given lambda, and the denominator is this marginal distribution for x. Right? The book points out that the key aspect is where is lambda in this. And so this thing ends up being so-called proportional to probability function over here is proportional to this parts that have lambda in them. And what's lambda in there? There was a lambda to the beta, no, lambda to the alpha minus 1 in the prior. There's an e to the negative beta lambda here. And in this one, there's a lambda to the x, e to the negative lambda shows up. There's some other combinatorics and multiplier things here, and there's this whole thing in the denominator where lambda is integrated out. But the shortcut to the answer is looking at these things. These particular choices of prior are called conjugate to one another because the prior and the likelihood use the parameters in the same forms. They're kind of popular choices because of that. And so this thing, if you multiply it together, is lambda to the x plus alpha minus 1, and then e to the negative these things. So there's a lambda and there's a beta plus 1 here. So if we get one observation, like the number of babies born on one day, the answer ends up being that after seeing that data point, we would be x plus alpha, is how that one would change. And this one just increments by 1, the being beta, 1 plus beta. And we get a new distribution, and we would say that we expect lambda, the expected value of lambda, is then now x plus alpha over 1 plus beta. And we would change our belief about the estimate from the prior one we got from asking, getting a few responses, to this new number. We're only likely to really want to base a decision on one data point, right? So we're going to have a bunch of days. So instead of depending on one x, we're really going to depend on a whole bunch of them. Right? So what we would do, we have x1, x2, xn that are independent observations. We want to get the posterior distribution of lambda given all of our x's. It follows the same initial probability step of Bayes' theorem for reversing things. So it still is the prior in there, which is one prior. And then there's the joint distribution of all the data given our parameter over the distribution of just these counts when lambda is integrated out and disappears from the formula. Again, this is proportional to the numerator because we will really only care where lambda is. And so it's a prior, and now this thing, I've left out the commas just because they're in there, is the likelihood based on those observations. Right? The likelihood piece of the x1, x2 up to xn given lambda is a product of the individual probabilities. They had a lambda to the xi, e to the negative lambda over xi factorial. And just like we did for likelihood things, maximum likelihood, right, we'll combine terms together where appropriate. And this thing is, we're going to ignore the xi factorials. They'll be in the numerator, they'll be in the denominator, they'll cancel in the base thing. But there's a lambda, the sum of the xi's, and there's an e to the negative n lambda. That's in there. So the lambda parts that are relevant here, well, there's lambda to the alpha minus 1, e to the negative beta lambda in the prior, and now the likelihood contributes lambda to the sum of the xi's, e to the negative m lambda. And we can combine those pieces. So we'll get lambda to the alpha plus the sum of the xi's minus 1. And then there's e to the negative beta plus n times lambda. Is there a minus 1
No?
in this? Yes, okay. Yeah, the beta to alpha, lambda to alpha minus 1. So now the posterior, so the answer ends up being, we haven't crossed all and dotted all the t's and done all the integration and figured that out exactly, but lambda given our data, this data set, x1, x2, up to xn ends up being a gamma random variable. Its parameters are alpha plus the sum of the xi's, right? And then this second one is beta plus n. So the posterior mean for lambda, the posterior expectation where we think it is going to be this lambda times the sum of xi's over the beta plus n. And this posterior mean can be kind of written as a combination of the prior, alpha over beta, and this like a sample average. Right? I don't have room to write it there really, but the mean was alpha plus the sum of the xi's and then beta plus n. This thing can be written as beta times alpha over beta. Right? That's alpha. And then n over x bar is the sum of the xi's over beta plus n. So the posterior mean, right after seeing our data, in this case, like the binomial one, happens to be, it's convenient to write it as a weighted average of the prior mean based on our initial guess and the data. And guess what? As the sample size gets bigger, whatever your prior was gets wiped away by the data that are coming forward. But smaller sample sizes, your personal input, right, has more of an impact. So what happens with our little story here, right? We had the alpha over beta was set to, what did we set it at?
36.6.
36.6, right? So here are some data that are coming in that I simulated from a Poisson based on what the website said. One day there were 5 births, and 4, and 8, and 4, and 8. So we have our first 5 days, give those numbers. Vermont's, not that big, but and so that's what it gives there. And then so the sum of these xi's is what we need.
So you're saying you shouldn't consult us as an expert.
Well, no, I mean, so something you do learn, right? You expect to say your prior opinions and things like that, and then it does get updated, right? So we are, that's that, and n is 5. All right, so if we put those things in there, right, this was our prior. We probably don't need to go up that high. So I'm going to set lambda down here to about 100, right? And so this is the prior, and I focused in on that 100. Now we had the sum was 29, right? And then this was 5. So this is going to go higher. As you crunch it in, the height has to go higher because the area has to stay 1. So it's always tricky to, so this would be the new prior. And we can put the old one, the prior, on here because it's lower. Make it color equals red. So there was our prior. But the data was all much lower. So quickly, just under 5 observations, right, it's pulled it back to be considered consistent there. Right? And the mean of, if you don't, the mean 4.39 plus 29 alpha over beta, 0.2 plus 5, is 6.52. The actual, 25 over 5, the observed average of just those 5 days is 5.8, but our posterior average is a little bit higher because it incorporates your prior opinion and this. What about if the next round of data comes in, you know, five more days, right? And so the next 5 days were 6, 7, 5, 9, and 9. And so that sum of these is 36. And we can add that in. We can start with the prior, you know, the distribution that the place that we're at after the first 5 days. Now we get 5 more days, so we can add these next 5 in. You could do 1 day at a time, but you know that's not going to change things all that much. And a supervisor probably doesn't want to report every day, so you know, wait for 5 days or something. So how does that change things? Now we have the next sum was 36. Right? We've added 5 more days, so that's going to, there's 5 more contributions to the likelihood. So there's e to the negative lambda 5 more times, and so it gets added in there. And so this is the posterior distribution now, tighter. And maybe let's change lambda again. Let's make lambda a little smaller. Let's make it up to about 20, up to about 40 or so. Right? Now this is the posterior distribution now. Right? 10 observations, all were pretty tight in here, and it's really kind of narrowed down into that as evidence of where we think the average is per day. The previous one, right here, if I put that on as points, oops, kind of funny. That's the prior. The prior was way out, right? This was before any data. It would have most of its probability way out there, so it looks a little funny there. The second one, I can just take this. Just take these two off. I'll make this one blue. Oops. We'll fix this. Okay. That's the current one. That's 2 data points. All right. This is the prior, and then this one is the points instead of plots. It doesn't be drawn. Right. So between the one with 5 data points and 10 data points, right? The blue one is 5 data points, and the black one was 10 data points. They're kind of in the same place, right? But we've had more data, so it's a little narrower, a little higher, a little more precise. It takes quite a bit of data to get more precise there, but that's the update. According to the website, there's 2,200 birth babies per year. And so 2,220 out of 365 days, about 6 per day. Right?
So a tenth of what we got.
About a tenth, right? Yeah, so we're a lot smaller than you think. In 2016, there were 5,734 babies born to mothers in Vermont. So, which is actually the lowest in decades. But that's how things get, updated. A little experience with that. On Friday, we'll do. We'll look at something like the data are exponential, perhaps, or maybe the data, right, are normal, and we want to know about some of these parameters. That's usually a lambda there. Bayesian models can be done with continuous data, with continuous priors. They can be done with 2 dimensions. You have to have a prior distribution on both of these things for it to work out. We'll mostly look at those as just illustrations. The homework that you have that's due on Friday does this beta binomial in a couple ways and stuff from the previous chapter. So. Okay.
I was able to do all the part of it, I was just confused. I need to essay
Heart rate. So, right, there's 57 zeros.
Yeah.
And these are bigger than 55.
Yeah.
Like you could say 57 times 0.
Oh, okay. And then 2 times 6.5.
Yeah.
Oh.
And then divide all that by 200, I think.
Okay.
Or maybe
Still 57 plus 2.
yeah.
And then within this section.
That's hard.
So like if you're in the categories 0, 1, 3, or 4.
0, 1, 2, 3, 4. Yeah.
So
So here's the
expected
observer,
count,
yes,
yeah.
observer, this, and this.
Okay.
And then that's the next observer count.
Uh,
For 14. So it's reducing this, the several categories just down.
down to 4, and so I don't, for the, that's the expected count, so I would just expect 57.
That's going to be the observer.
Okay. And
So-
then how would you calculate, would expected since there's 6 categories? Or 7 categories? Could you say 7?
Well, you're going to use the Poisson probability.
Okay.
I think there's an R code.
There might be, I did this like Monday.
So if you have the density for a Poisson, the chance that
Yeah.
it's 0 with a rate of 0.99 ends up being 37%.
Oh, so I just use that
Use that
to for
percent,
expected?
and then if there's 100 or 90, you know, how many ever cases
Yeah.
there are, you know, so if there were 99, you'd expect 37, 36.7, so
Okay.
be there. So you can do that for 0, 1, and 2, but 3 plus is going to be everything else.
Okay. All right. Thank you.
Yep. Yes.
Just reminding you that I
You're
will
going to be
not
gone.
be here.
Okay.
I'm gone 22nd to the 2nd, so I'll be missing Friday.
Skiing the whole time? or-
Yeah.
Okay.
I'll be missing Friday, Monday, and then the following Monday.
Okay. Okay.
So,
Oh, the following Monday too, okay.
yeah, that
Yep.
first day of classes, we're all.
So we won't have class on the Monday of the Thanksgiving week, so there's nothing
Okay,
going
perfect.
there.
Awesome.
You know, there's the project
Chipping
to
away.
do,
Yep.
and I'm considering what to do for one last homework, because we've had something on Bay that might be kind of a
Mhm.
review type homework or
I
something.
can't believe we're almost there. We're almost done.
Yeah.
That's crazy.
Yeah, so
Okay.
Friday, and then since there's nothing that next week, yeah, then 3 more days.
Yeah, I know,
4 days,
seriously.
yeah.
All right, I'll see you in 2 Wednesdays.
Yeah, have a good time. Are you skiing? Where are
Out
you?
west.
Out west?
We're out in Colorado.
Ah,
Yeah.
exciting. So,
Yeah, happy Thanksgiving. Have a good one.
Happy Thanksgiving.